Every growth marketer knows the pain. You buy 1,000 clicks, 90% evaporate the moment the interface asks for a browser extension. 12 secret words and a second device to back them up. You can cut the friction with a custodial login with email, but then you own the user's keys and the legal liability. ZK Login tackles both issues in one stroke. The user signs in with an identity provider they already trust. Google, Apple, Discord, you name it. In the background, their browser crafts a zero-knowledge proof that says, I own a valid ID token for this account right now, yet reveals neither the email nor the JWT. Validators verify that proof on-chain and deterministically derive a SUI address tied to the user's identity hash. The result: the user never installs a wallet or touches a seed phrase, but still ends up with a fully self-custodial account that only they can control. You keep funnel conversion, they keep sovereignty. Let's zoom into the cryptography. Step 1 is pure OAuth. Your front end redirects to Google, the user hits allow, and Google returns a JSON web token signed with its private key. Step 2 is where the magic starts. The browser feeds that JWT into a WebAssembly module that implements a proven SNARK circuit. The circuit checks the token's signature against Google's public key and verifies claims like expiry and audience. Crucially, the circuit outputs only a succinct proof, plus a few 80-byte public inputs, a hash of the token, the issuer's key hash, and a random salt the user chooses. Those inputs, together with the proof, travel inside the transaction's authenticator field. Every validator runs a constant time verification routine. If the proof passes and the epoch is within range, they hash the tuple, issuer, user hash, salt, into a 32-byte SUI address, exactly as they'd hash an ED25519 pub key. The transaction then executes with that address as sender. The user's private OAuth session never leaves the device, yet the blockchain now recognizes a brand new self-custodial account. Reverse. Each proof embeds the current epoch plus a random nonce. Replay the same proof 1 minute later, and it fails. Validators compare the epoch they hash inside the circuit to the epoch and block metadata. To hijack an account, an adversary must steal or forge a live Google token and generate a convincing snark, a 1 in 2 to the power of 128 shot, even before rate limits. Should the user worry an ex-employee knows their old salt? They simply pick a new salt, redo ZK login, and move assets. The previous address becomes inert. Later, power users can export the generated private key. Yes, there is still a key pair under the hood, and import it into a ledger or SUI wallet, keeping the same on-chain address and history. Implementation is pleasantly light. Add mistins at mistin/zycologan package to your React or Next.js app. In Google Cloud Console, create an OAuth client. Choose web, set your domain, and /OAuth2/callback as redirect. In code, you call Google's SDK getID token, then hand that string to generate proof. 2 parameters matter: the JWT itself and max epoch. Essentially, proof expires after block n. The helper spins up a WASM-based Groth16 prover and returns a binary proof plus a struct of public inputs. Pass those into Build's login signer. The helper derives the deterministic address off-chain and prepares a signer object with the right authenticator type. Build your transaction block exactly like before. Call badge::claim, for instance. Then sign and execute. On the back end, you might persist a mapping from address to OAuth sub for password reset flows, but that's optional. Finally, expose a settings page where advanced users export their key store. The library hands you an encrypted JSON, compatible with every SUI wallet. Yes, zero knowledge isn't free. Verifying a Groth 16 proof costs roughly 950 compute units versus 400 for a classic ED 25519 signature. At today's mainnet pricing, that's maybe 1 cent instead of half a cent. Negligible next to swap slippage. Client side, the heavy lift is proof generation, approximately 600 milliseconds on Apple M1, plus or minus 1.5 seconds on a modern iPhone. Show a friendly spinner. Users tolerate sub 2-second waits far more than Chrome extension installs. Because the proof authenticates the whole transaction, you can pack several move calls, mint, list, vote, in the same block and pay the verifier cost once. Miston's roadmap includes recursive aggregation. Dozens of user proofs collapsed into one before they reach validators, cutting server gas and bandwidth by an order of magnitude. Think of ZK Login as onboarding on easy mode. The moment a user claims their first badge, they already have full on-chain ownership. They could even trade on the marketplace. Yet power users may want a browser extension for DApp compatibility or a ledger for cold storage. Offer a one-click banner. Upgrade security. Behind that button, 2 branches. Export. The library encrypts the private key with a password, downloads a JSON key store, the user imports it into SUI wallet and keeps the same address, meaning all their capabilities, listing cap, mint cap, still work without extra on-chain rights. Migrate. Generate a brand new ED25519 address. Build a move transaction that transfers badges, tokens, and caps, then instruct the user to sign both with a ZK login as sender and the extension as recipient. Either path completes the funnel without weird edge cases. Here's a complete flow in about 40 lines. After OAuth, we call generate proof. The heavy WebAssembly chunk runs in a web worker so it won't freeze the UI thread. We pass max epoch set a week in the future, long enough for mobile users on flaky networks, yet short enough to limit replay risk. Build ZK Login Signer gives us an object that mirrors the API of a classic key pair signer. Address, sign, and execute. We build a transaction block for our badge. Josh, claim entry, set the sender, and fire. The helper automatically fills the authenticator with the proof bytes and public inputs. On full node RPC, you'll see auth type, ZK login, but the rest of the transaction looks ordinary. The console logs transaction digest and final status as soon as the validator commits. Smart contracts are blissfully unaware of authenticator types. The VM maps every valid signature or proof to a sender address, and that's all your move code sees. Your existing badge. Claim function just works. If, however, you want analytics on how many users entered via ZK login versus ledger, emit a tiny onboard event. The front end passes auth type as a byte vector, and dashboards can chart adoption over time. Gas overhead is microscopic. One event struct cost maybe 40 compute units, far less than a log line. Even though the scenario harness can't run a real snark, we can still mimic a ZK login address by starting the scenario with any 0x prefixed value. We invoke badge : claim, commit a block, and verify the badge sits in that address's storage. This proves that nothing in our move code path depends on the cryptography behind the authenticator. If someone later refactors claim to check an allow list of ED25519 pub keys, this test will turn red, signaling they just broke ZK login onboarding.